What's going on YouTube? I believe that we are live now. Welcome back to my practice stream. Today is going to be our second discussion stream on Basic Mathematics by Serge Lang, this really lovely book. I see we've got a bunch of people who have signed up for the hobbyist tier membership. Thank you everybody so much. I imagine that some people will be able to join live, and then other people will be watching this video after the fact. So if you are watching this after the fact, thank you. Thank you for watching. Please leave a comment in the comment section and let me know. We may try to move this around and find another time if this time is like impossible for people. What else do I want to say? First off, this discussion session, will be working some problems from section 3 on multiplication. We may revisit a little bit about addition, and we might just add in some other topics. I could give a sneak peek to some other ideas, some other topics that are in the book, some things that are outside of the book. We can also review and talk about some of the examples from the previous video. As of today, I suppose if somebody's watching the VOD, as of today we have 5 episodes in the series. Episodes 1, 2, 3, 4, and 5. We just dropped episode 5 and episode 4. These are both on multiplication. But the way that I'm structuring things is every week we're going to do one section of the book and 3 videos. 1 theory video, 1 examples video, and 1 discussion stream. So right now we're watching a discussion. And if nobody shows up, I will just be working problems and talking about some things, like just give a little more detail, especially examples that just didn't fit in the examples video that we just posted. So if you haven't watched these already and you are watching this, I think it would really benefit you if you wanted to pause this video and go watch episodes 4 and 5 first. But if you're here live, of course, just say hi and we'll talk about whatever people want. I'll take questions if people want a specific exercise to be worked. I'm happy to do that. Really, this is your time, is how I see it. I have ideas of how I would use this time if we don't have questions. But hey, we got somebody in the chat. What's up, Tau family? HHH Tau family, how's it going? Let's let in Luna. How's it going? Hey, and we got Jack Mack too. What's up, Jack Mack? Great to see you. Okay, so I was just talking about how we've done a few episodes. I wonder, have y'all had a chance to watch episode 5 yet? It just dropped like 2 days ago, and I know that these are long 40-minute videos, so really just overall, like, I want to leave it up to you all. Do you have questions? Is there any kind of specific topic you all want to talk about? Anything that you're confused about with the recent videos that you'd like me to work again, either from the theory or from the examples? I feel that the priority today could be section 3 on multiplication, but we could also go back and talk in more depth about addition, about section 2, or if people want, we could just move on and start adding some new topics. Not yet, but you did work through section 1.3. Awesome. Definitely do watch episode 5. In my examples videos, every week I want 3 videos: theory, examples, and discussion. We're in a discussion right now. In the examples video, I'll be adding a lot of topics and math topics that are not in Lang at all. So do watch episode 5, even if you've already worked through section 1.3. If you've worked through 1.3, you can probably skip the theory video. The theory videos are going to be very close to Lang, but the examples videos I'm going to be bringing in other ideas. And there's something I'm really proud about in episode 5 that I'd like to talk about at some point. Cool. All right. So if we don't have any specific questions yet, I wanted to just get started on this exercise maybe. How are you all finding the exercises? Like, you worked through section 1.3. Did you work the exercises? And pretty easygoing so far? I can find some additional resources for people who want more. Like, if you're finding these sections a little too easy or something, or you're getting through it too fast, I've got other books that'll talk about the same exact topics, but they're a little deeper, like a little harder. Yeah, that's just one way to treat this course. All right, so proof, section 1.3 exercise 3. Let's obtain an expression for a plus b to the fourth and a minus b to the fourth, similar to exercise 1.3.2. So, recall from the section, Lang called this poetry. I think it's poetry. I think he's right. A squared plus 2ab plus b squared. So we have that. And then exercise 2, I don't remember if I worked this on the video or not. I worked it somewhere, maybe in a stream recently. But this exercise, he asks you to show, he tells you what the solution is for this. Or what the identity is. It's a cubed plus 3ab plus 3a squared b plus 3ab squared plus b cubed. I'll just focus right now in this practice session just on the sum formulas, and you could try the difference formulas. So, in the theory video, I worked a minus b squared. I remember that. Okay, so exercise 1.3.2 tells you to prove this. And, well, you can do it ultimately by distributive property. A plus b quantity cubed is a plus b multiplied by itself 3 times, by definition of a power of a thing. A power of a thing means multiplying it by itself that many times. So, by definition of, I'm going to use different labels, x to the n, to avoid overloading, reusing the term a, because by definition of an exponent. Okay. Well, by definition, again, these two, the right two, are a plus b squared, right? And a plus b squared times a plus b is now in a format where we can use the distributive property. So this is by the distributive property. And then you unpeel this a little bit. You use commutativity and associativity. You just work through that, substituting. Use this substitution at this step, and then do distributivity, and then you end up getting to the desired right-hand side. So I'm going to pause at this point. I've already written down the key ideas in this proof. So I want you to try to fill in those details. If anybody has any questions about these first steps, then please let me know, and I'll pause and elaborate more. But That's a key idea to prove the previous exercise. Now, in this exercise, Lang wants us to find the expressions for the sum to the fourth power of a sum. The fourth power of a sum. By definition, a plus b to the fourth is a plus b multiplied by itself 4 times, right? This is the definition of the power of a number, multiplying by itself that many times. Well, I see 2 proofs on this. I'm going to do this, and then I'm going to draw an arrow and remind myself I can go a different direction. I think that the most clear approach that I see is that I can fold all 3 of these as a plus b quantity cubed. And now we can use distributivity. Slowing down for a second to make sure everybody sees what I'm talking about. I'm using a substitution, maybe x or z or c. I guess I could call a plus b cubed. Let's call that c. All of this is c now. Then the distributive property says, the right distributive property says that this is equal to AC plus BC. Because this property holds for any number, and this is ultimately a number. A plus B quantity cubed. So now that's the form of this next line. So I want to make sure people see that step of how I'm doing this distributive step. We've done it a few times, but still, it's really valuable to repeat it. Now we can substitute the formula that we previously proved, that the cube of a sum is this complex thing. The cube of a sum is that, and you can substitute that in here and then use distributivity and do a bunch of steps and then end up getting to the right-hand side. I'm just going to say right-hand side for the correct expression. I want to show another proof that I'd actually prefer, that I feel is like just slightly a little more elegant. Somehow I just feel that this one is just a little more, well, I suppose it needs another idea. Well, okay. What I want to show is that a plus b to the fourth is by definition a plus b multiplied by itself 4 times. This doesn't take too long to rewrite. Okay, well, instead of folding all 3 of these as a plus b cubed, I could do 2. We could say that this is a plus b squared times a plus b squared, right? So this is just a different argument. And now this one does not depend now on the previous exercise. Now this argument, this approach that I'm taking, does not require that we've seen a plus, the cube of a sum. It only depends on the square of a sum, which was in the text. Okay. Now, we can now use associativity. or sorry, not associativity, distributivity. We do technically need a triple distributivity. So maybe we would want to prove this for ourselves, and you can do it step by step using substitutions again. But you'll prove for yourself, if you do this, the property that we all know and love called foiling. So we've all learned this, I think, in grade school or in earlier math classes. You multiply each term by each term, distributing one at a time, right? And then, I don't know, it's a little complicated looking with two trinomials, but this is now distributivity of two trinomials. You can prove that this method works for yourself by repeating associativity and the distributive property. So we could say that this is in the form A plus B times C. Like if A is A1, B is A2 plus A3, and C is all of the right-hand side, or the second trinomial, then knowing that this is AC plus BC says that this distribution is going to be A1 times B1 plus B2 plus B3 plus A2 plus A3 times B1 plus B2 plus B3 equals ... You continue doing this process, like distributing one step at a time until we get the entire combinations, which we call foiling. So I just wanted to give a little argument for why this approach works, but it behaves exactly as we've learned and that we're used to. I'm going to multiply a squared times this entire term plus 2ab times that entire term, or that entire sum, and b squared times the entire thing. So this is, again, distributive property. Now I can distribute each of these, and the first ends up being a to the fourth plus 2a cubed b. I used commutativity, notice. A squared times 2ab equals 2a cubed times b plus a squared b squared plus 2a cubed b plus 4a squared b squared plus 2ab cubed plus a squared b squared. I used commutativity. I'm distributing this b squared into those terms. A squared b squared plus 2ab cubed plus b to the fourth. Now I have all of the individual terms, and I can combine like terms. I look for all the a to the fourth terms. This is the only one. A to the fourth. Next, I'm going to work this in a sorted way. A to the fourth and a cubes. Those are the only two a cubed terms. A to the fourth plus 4. Oops. A cubed. A cubed b, that is. Now I'm going to look for all the a squared terms. Which we've got 1 plus 4 plus 1. There are 6 of them. Then we're going to look for all of the a to the first power terms. This one, and this one. So that would be 4ab cubed after you add them together, plus b to the fourth. And this is now our identity. A plus b to the fourth is a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. And voila, we are done. We've found our formula that we're looking for. Any questions? Or thoughts or feedback or anything? If not, that's okay. We can move on. There's one exercise. That's half of exercise 4. The fourth power of a difference is extremely similar. It's really the same proof idea and process. Easy peasy. That's great. Great to hear. Yeah. Right now, these proofs have not yet gotten too crunchy. They're not too hard yet. I want to quickly just mention in episode 5. In episode 5, I introduced this problem, and you'll see what it's called and whatnot if you watch that episode. I won't take too much of the time here because I would just be repeating the same thing. There's a hidden secret in this, okay? I hid a really amazing fact in this problem and the way that I presented it in episode 5, and I'm honestly kind of proud of it. I kind of want to talk about it in my interviews coming up. So there's a hidden secret or a hidden math fact. There's a hidden discovery that you can find. A hidden discovery. If you want to find it for yourself or try to find it, don't read the comment section. If you want to find it on your own. It's completely up to you, of course. Like, this is just kind of an extra credit, bonus secret thing for somebody who might be looking for this thing. There's a really interesting math fact that I carefully guided one viewer who found it, and they commented about it. So it's up to you. You know, if you want to look for it, you can, or if you just want to read the comment section, you can. It's completely up to you. Just letting you know, there's spoilers in the comment section for anybody who might want to find it. What is going on? I just got some audio, like a video just started playing, but okay. All right, nothing. All right, weird. Okay, so just FYI, there's some spoilers in there. I could introduce the problem now. I kind of want to do something else. I really don't think that the other exercises in section 3 are that interesting. I think that you all can work them. I don't want to assume, of course. So if anybody has any questions, please let me know. There are no dumb questions. I think that the rest of the questions you'll be able to solve based on, especially if you just followed the proof that I just did on the, if you're able to follow this proof on the fourth power of a sum, then I think that the rest of the problems in the exercise set are not too hard. Or like, it's not that they're not too hard. Like, any of this is hard at some point for somebody's journey. But I think that we've got enough examples in this video, is what I'm trying to say. So we could start looking at something new. I want to test this with you all. Here's something brand new, I think. I'm going to jump way ahead. If you all want, I can show a new topic, unless anybody wants. If Tau Family or Jack Mac want a specific topic, I could do that. But I kind of want to test the idea of my next video is going to be on induction. So I'm going to jump all the way from chapter 1, section 1.3 to 16.1. We're going to jump all the way to page 383. Trust me, there's a method to the madness here. And you all can be my guinea pigs. You can see the sneak peek and let me know if you think that we're ready to do this section next. You all can tell me if you think we should do this section for the next week's videos. Okay. I don't have a physical set of dominoes right now, unfortunately. But, you know, I've seen this concept explained as dominoes so many times in so many lectures from math professors, and they've never had a physical set of dominoes, so it's fine. I want to get one for the video, but imagine that you have a bunch of dominoes all lined up together. So imagine that these are dominoes, not the pizza, but the little tiles, dominoes. Maybe we have a few more over here, right? If you knock over the first domino, then based on this, all these first ones are really close together. So if I knock over the first one, then all of those are going to fall and knock over the next one. But here there's a bigger gap, right? And knocking over the first domino does not continue knocking down the future dominoes. This is the analogy that we want to have in mind for induction. In math, there are some statements. We're going to call it a proposition, which is like a mathematical statement which is either true or false. Like a mathematical sentence is either true or false. 2 plus 2 equals 4. This is true. Usually. 2 plus 3 equals 4. This is false. Right? Let's see. 0 raised to n equals 0 for all integers n. Right? So this is a mathematical sentence. It's false. I tricked you, maybe. Like, it looks like it's true. It's not. 0 to the 0 is undefined. 0 to the 0 is undefined, but otherwise 0 raised to any other number is true. So what I could do is I could change this and say for all n not equal to 0, now I fixed it. And now this sentence is true, right? So let P of n mean the sentence or the statement, the proposition is true for the number n. Then what we wrote earlier of a bunch of dominoes that are all lined up. Maybe this was n equal 1, 2, 3, 4, 5, and then there's a big gap, 6, 7, 8, 9, 10. Right? Now, I can think of this dominoes example that I had as P of 1 is true, implies that P of 2 is true. Knocking over 1 knocks over 2, and then that knocks over 3, and then that knocks over 4, and then that knocks over 5. Right? Because each of these are close together. All of those dominoes are close to each other. So if I can show that some math statement is true for 1, in this case, it automatically shows that it's true for 2, 3, 4, and 5. But we've got a big gap here, so if I wanted to show it was true for all of the numbers, what I could do is show that it's true for 1, and I could show that it's true for 6, which knocks over 7, knocks over 8, knocks over 9, knocks over 10. We're going to get a little more concrete here. Right now, I'm still speaking in analogies somewhat, even though this is more mathematically precise already. We started with the analogy, and now I'm talking about a mathematical statement, a proposition that's either true or false, and one implying the next in a list. So we're getting a little closer to the precise mathematical definition of induction. I just want to jump right to the general idea. A proof by induction. Please let me know in the chat who has seen proof by induction already and who hasn't. Has anybody here seen it already? And has anybody not seen it? Both of those are very valuable to me because I'd love to know from those who have seen it, how's this explanation? You have, but many years ago. Okay, many years ago. Nice, great. So I wonder if you remember where this is going, what my first example might be, there's a very standard first example that I'm excited to share with you all. A proof by induction has two steps. One, show typically that P of 1 is true. This is called the base case. This is like saying I can knock over the first domino. So step 1 is prove that the first domino will fall. Like it's that the domino imagery is just excellent. It's just such an excellent metaphor. It's why we always use it to teach this concept, I think. The base case shows that the proposition is true for the first in a list. It doesn't always have to start at 1. It can start at a different number, but for simplicity, we'll start at 1. We'll just assume that we're proving something for n equals 1. This is step 1. And then step 2, show that anytime if you assume P of n is true, then P of n plus 1 is true. So now I'm using the same notation that I was introducing earlier. Show that if in a long list of dominoes, I'm zoomed in, I have no idea about any gaps before or not, I'm zoomed in, and I have shown that every single domino is close together. I have no clue what number I am in the universe of numbers. If I show that every domino is close enough to the next one, then anytime that the thing is true for the nth, then it's true for the next one as well. This is like proving that every domino is close to the next domino. Then you have an infinite list of dominoes, an infinite list of mathematical statements. This is like P of 0 is true, therefore P1 is true, therefore P2 is true, therefore P3 is true, therefore ... This chain just keeps going on for every single number. So this is the inductive step. This is called the inductive step. Every domino is close to the next one. This inductive step and the base case together, one of them, you prove that all the dominoes are close together, and then another step is you prove that you knock over the first one. Therefore, the entire infinity of dominoes will fall. Okay, so this is the strategy of a proof by induction. We have these two steps. So now, I wonder if you all know any guesses what the first ever canonical standard example that we always show by induction. I'm going to give it 5 seconds just to make sure I force you all to try to think of it. And if you don't know it, it's totally okay. It's something we've seen already. N equals 1. Well, yeah, but n equals 1, what is... Yeah, we want to show something is true for 1. And if it's true for one number, then it's true for the next number. This is the idea. The base case and the inductive step. But now my question is, what is our math claim proposition P? Which one am I thinking of? What is our math proposition P? What's the first example that I'm going to prove by induction? And it looks like we don't know what it is, and that's okay. Remember this one? 1 plus 2 plus ... Here, let me make this ever so slightly more mathematically precise. 1 plus 2 plus 3 plus ... n is n times n plus 1 divided by 2. So we're coming back to the same exact example. We proved this by Gauss's beautiful trick. We proved it by Gauss's argument, but we can also prove this one by induction. So we're going to see a secondary proof for this. Proof. First, we show the claim is true for n equal 1. The left-hand side is just 1. It's the only number in that list. And maybe I could even say 1 plus ... n is just 1. Because n is 1. That's kind of hard to write down and make precise. Any book would typically just say, first we show the claim is true for n equals 1. The left-hand side of the equality is 1 because it only has one term in it because n is 1. So it only has 1. The right-hand side is then, if n is 1, the right-hand side is 1 times 1 plus 1 divided by 2, which is 1 times 2 divided by 2, which is 2 divided by 2, which is 1. Thus, the claim is true for n equal 1, right? This formula works when n is 1. Usually the base case like this is always typically pretty easy to show. Typically, the hard part is step 2. Step 2, the inductive step, is harder, usually. Next, we show the inductive step is true. Here, we assume that P of n is true, i.e., that 1 plus ... n is equal to n times n plus 1 over 2. Then we prove that the statement is true for the next number as well. The statement would say that the sum of the first n plus 1 integers is equal to a slightly modified version of the right-hand side. So I could put maybe like this left-hand side equals question mark. If n is now n plus 1, we have n plus 1, n plus 1 plus 1 is n plus 2. divided by 2. This is what we want to show. So maybe I could refactor this and say, we prove P of n plus 1 is true by showing that this statement is true. Thus, let's take a look. 1 plus ... n plus n plus 1. We want to prove that sentence. This is our goal right now. In some modern math programming stuff, we call this a goal. Our goal is to show that this sentence is true. Well, the left-hand side is this, and by assumption, the first n is, we assume that it is, that the sentence was true for P of n. It's true up to the point n. So this is n times n plus 1 over 2 plus n plus 1. By assumption of, we assume that the claim is true for n numbers, for all the dominoes up to the domino that you're at, any random domino. And now we show that this new random domino is close enough to the previous one. So we factor, or we distribute that n. And now n plus 1, I can rewrite this way. And now I have a common denominator. So I can add the terms. In the numerator, n squared plus n plus 2n plus 2. Okay, divided by 2. Combining like terms, we have n squared plus 3n plus 2 divided by 2. And now, the numerator, voila, check this out. The numerator factors exactly how we want it to. The numerator factors as n plus 1 times n plus 2. Therefore, the claim is also true for n plus 1. So the inductive step is complete, and therefore, so it is true for all integers n. This one's a little different, like a little trickier, and it may take a couple of times seeing this or working these on your own to get the hang of it. I feel that this is a very different proof technique than most people have seen before. But this is one of the most powerful proof techniques that we have. Often when we have an identity or we have some sort of mathematical claim about the numbers, we often prove it by induction through this process of showing the base case and then showing the inductive step. So P of 1 is true. You show that's true. And then part 2, you show that anytime 1 is true, anytime that the claim is true for a number, then it's true for the next number as well. Those two combined get you the claim is true for 1 and 2 and 3 and 4 and ... forever. Any questions or feedback? Temperature check. Like, 1 to 10, how confused are you all? It's hard to read, faces and things like that in a live stream, but I would love to know if you all think that I could, maybe with maybe one more private practice rep or something, try to use this as the next section in the video series. Can you highlight some problems that involve this proof style so we can do it ourselves? Absolutely. Yeah, that's a great question. I won't do it. I won't work this example unless you want me to, but the next standard example after that, guess what? There's also a really cool formula for the sum of the square numbers. I don't even remember it off the top of my head, to be honest. So this would be your homework, and I think it's the first exercise in Lang. I think I remember it, but I don't want to misspeak. I think it's n plus 1 times n plus 2 times 2n plus 1 or something. I always forget this one. Okay, it's exercise 2. His exercise 1 is fantastic. I love exercise 1. We should have done this one. Oh well. Exercise 2. I'll just say that this one is Lang exercise 16.1.2. Prove that this is n times n plus 1 times 2n plus 1. I was extremely close, if not exactly right. I remember that it was a 2n plus or minus 1 divided by 6. I don't think I would have ever found this one. Maybe in my head, I can try to remember this as n times n plus 1 divided by 2 times 2n plus 1 divided by 3. By factoring, you can see that these two are the same. So now this one, this term is, I can remember it from there, and now maybe all I have to remember is this part. But in any case, you want to try to work this exercise to show that the sum of squares is this formula. And it's almost the same exact process. I'll give you the easiest part. The easy part is the base case. When n equals 1, 1 squared, does 1 squared equal 1 times 1 plus 1 times 2 times 1 plus 1 over 6? This is true if and only if 1 equals 1 times 2 times 2 plus 1 is 3 divided by 6, and yes, this is true. So, if you were to write this like a little more cleanly, like a little more formally, I'd say when n is 1, the left-hand side is 1 squared, which is just 1. And the right-hand side is 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6, which equals, as I just showed, 1. So the base case is true. So the statement is true. for n equal 1. The base case is satisfied, is another way to say this. Next, assume that 1 squared plus ... is this. And you want to show the statement is true for n plus 1. So everywhere in the statement where you are referring to an n, it should be referring to n plus 1. And you check that the left-hand side ends up equaling the right-hand side, substituting n plus 1. I think that's enough of a hint. That's a good one. And then another excellent hint comes back to, just like in my, I use Gauss's, this is the sum of n odd integers. The first two odd integers are 1 plus and 3. And if you add those, 1 plus 3 equals 4. 1 plus 3 plus 5 equals 9. 1 plus 3 plus 5 plus 7 equals 16. You all might remember that I claimed that this always equals n squared. You can prove this by induction as well. This is another classic example of something that you can show by induction. So again, clearly, base case is true. Oftentimes in a math book, you will just see the author say base case is true, or it's clearly true when n is 1 or something. And we can see that. The left-hand side is just 1, and then the right-hand side is 1 squared, which is 1. It's a little overkill to write out the base case sometimes. It's a little tedious. We can see that the base case is true because the left-hand side only has one number, 1. The right-hand side is 1 squared, which is 1. So they are equal. Next, you assume that the claim is true for P of n. Now we show that the claim is true for n plus 1. i.e., you want to show that 1 plus 3 plus ... plus 2n minus 1 plus the next odd integer equals... So you want to do this work where I put some dots, where I put those ellipses. You want to show that that ends up equaling n plus 1 quantity squared. Questions, thoughts, feedback? Do you think that we're ready to jump right to this type of proof technique for the next video? What I think I would do if I do this is I would introduce induction. I would work Gauss's. I would work the sum of n integers. This is a secondary proof. That's an alternative to Gauss's proof. And then I think I would prove this one. I think I would also do this one and worked out with in the video. Okay, yes, with some practice. It just takes practice, like anything else. So I think I could do this one in the next video, which is, suddenly jumping all the way to the end of this book, kind of. But really, this this course, this series, is not a course on pre-calculus. This is a course on intro to pure math, intro to proofs. And most of the math that we're talking about is high school pre-calculus math. But pre-calculus is not the goal. Proofs and pure math is the goal. And in many other books, in your very first section of an intro to proofs book, the very first section of this book is induction. Section 1.1, principle of mathematical induction. And the very first example that they give in this one is also Gauss's identity, or the triangle numbers. There are some other really incredibly beautiful, cool identities. Last year, I had a video early in my channel. Let me remember it. I think it's this. I have a whole video talking about this, and I call this a beautiful 2025 fact. So I could talk. No, this would be like my demo video, actually, my examples video on Thursday or something. This isn't, it's just so lovely. This one is just really kind of somewhat awe-inspiring. To me, because I'm a geek, as you all know. This fact is true in general. The sum of the first n cubes equals the sum of the first n integers quantity squared. There's nothing special about the number 9 in this identity other than the fact that it builds the last year's number 2025. Let me double check that I didn't get it backwards. 1 plus ... 9 quantity squared. By Gauss's, or by the triangle number identity, we know that would be 9 times 10 divided by 2. And then we want to square that number. So 10 divided by 2 is 5. So we have 5 times 9 squared. This is, if I want to get really fancy, 5 times 3 squared quantity squared. And now this is 3 to the 4th times 5 squared. Let's do this as, what is 3 to the 4th? That's 81. Yeah, 3 times 3 is 9, times 3 is 27, times 3 is 81. 81 times 25. What's the best way to do this one? Yeah, 25 times 8 is 200, so then 25 times 80, yep. 25 times 80 is 2,000. Plus distribute the 25. This is 2025. That's kind of cool. I think that's kind of cool. So I only showed the right-hand side, but you can work the left-hand side if you want to prove that for yourself. That 1 cubed plus 2 cubed, just to see this example as one example of practicing addition, practicing cubing. Dude, it's not the worst way to spend, 30 minutes. It might take you 30 minutes for this one, I don't know. Because that's a lot of cubes to add together. But 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 cubed. Now we're getting into some trickier territory. 4 cubed. 2 squared cubed. This is 2 to the 6th. I rewrote 4 as 2 squared and then cubed that, and I used the power of a power property to say that's 2 to the 5th. I have, 2 to the 6th. I have 2 to the 5th memorized. This one is just in my head. 2 to the 5th is 32, so then 2 to the 6th would be double that. It's 64. 5 cubed is 25 times 5, which is $1.25. $1.25, 125. 6 cubed. Let's see. 6 cubed is 2 times 3 cubed, which is going to be 2 cubed times 3 cubed. So with this, I could double 27 and then double it again and then double it again to get 216. I don't know if I've ever tried this. 7 cubed, I don't know if I have any cool tricks on that one. I mean, I guess 7 cubed, we can use our sum cubed formula to say that this is 5 cubed plus 3 times 5 squared times 2 plus 3 times 5 times 2 squared plus 2 cubed. That's a little crazy. I mean, it's not hard. We could finish that. This is 125 plus 6 times 25 is 150. 15 times 4 is 60 and 8. This is 275 plus 68. 75 plus 60 would be 75 plus 60, 335. 335 plus 8 would be 343. Dang, okay. 343. Or, of course, 7 cubed is 7 squared times 7 is 49 times 7. I saw this one earlier. This is an easier one. 50 minus 1 times 7. 5 times 7 is 35, so we get this, minus 7. This is 343. Is that what I wrote? Yeah. I got it both ways. Look at that. 343. 8 cubed. We're kind of in overtime. If anybody has any last questions or anything, I'd love to answer anything, but no worries. 8 cubed is... Well, 8 is the same as 2 cubed. So this, by our properties, is 2 to the 9th. Just like I have 2 to the 5th memorized, I have 2 to the 10th memorized. So then 2 to the 9th is half of that. Yep, 512 is 8 cubed. And 9 cubed, 9 cubed is 3 squared cubed is 3 to the 6th is maybe 3 cubed times 3 cubed is 27 times 27. I could do this as 25 plus 2. This is, like, I just refuse if I can avoid it, I refuse to use the table method unless I absolutely have to. 25 times 25 is 625. Oh, you have a proof question on page 24. Absolutely. Let me just wrap this up very, very rapidly. 4 times 25 is 100, and for this would be 700 and 729? Is that really true? And then supposedly, if you add all those numbers together, they should equal 2025 as well. You have a proof question on page 24. Yes. Let's take that and then we'll wrap up for today. Page 24. Do you want to... Oh, you're already looking into section 4 on divisibility. Heck yeah. Which one are you wondering about? Theorem 2? Or do you want to write out your question? I haven't read this section yet, if I'm honest. I've skimmed it. Let a be a positive integer. If a is even, then a squared is even. If a is odd, then a squared is odd. Is that... Oh, okay, great. Yes, excellent question. One question that you have is, what is the difference of a theorem versus a corollary? Great question. In math, all of these terms are somewhat arbitrary. They're somewhat organizational. They're more about what is the roadmap. Which math facts do we consider most important? Which ones are more beautiful? Which ones are just a stepping stone to another one? That type is called a lemma, which this book hasn't used yet. But to answer your question, a corollary is an easy result from a theorem. If you prove the hard thing, if you prove the theorem, then this is a specific example. One that came up earlier was -1 times a is negative a in one of the previous sections, in multiplication. And Lang didn't say this, but I pointed it out in my video that a corollary of this is specifically for the number -1. This is negative of -1, which in the past we've already shown is 1. This was a fact that we found previously. I think it's N4 or something. But therefore, a corollary is that -1 times itself is +1. This is a corollary, a specific example of this more general theorem. So on this one, a corollary, let a be a positive integer. If a squared is even, then a is even. If a squared is odd, then a is odd. I see, yeah. So it's just a reformulation. If a is even, then a squared is even. If a is odd, then a squared is odd. So every number is either even or odd. So, okay. Yes, so now you're asking about his specific logic on why is this a corollary? Okay. Yeah, let me try to explain that. So I haven't read this much, but I see it on this, I think. So Theorem 2 says, if a is a positive integer, then technically I should say a greater than 0 if it's positive. But if a is even, then a squared is even. If a is odd, a squared is odd. Okay, so this you can read his proof and hopefully believe it. And now your question is, how do we show that this corollary is a result of it? Corollary. If a squared is even, then a is even. If a squared is odd, a is odd. Okay. Well, to prove this corollary, proof. These are really two cases. Case one. Assume a squared is even. Then a is either, every number is either even or odd, right? By the theorem, a must be even, otherwise a squared would be odd. I think that that's a pretty reasonable kind of way to fill in the details here. Assuming a squared is even, the theorem tells us that a must be even, because if it weren't even, then a squared would be odd. And the second case is almost identical, just swapping even and odd everywhere. So assume a squared is odd, then a must be odd, otherwise a is even, so a squared is even. Okay, so reformulation. The corollary says if a squared is even, then a is even. The reformulation doesn't make sense. I thought he was going to use the contrapositive of the statement. I was going to say it's quite... Contrapositive says that if you have two statements, P and Q, this is proving this is equivalent to saying that not Q implies not P. This is what the contrapositive argument is. These two are equivalent. To prove P implies Q is to say that not Q implies not P. I think that, yeah, his framing, the way he said that it's a reformulation is vague and a little hard to understand why it's equivalent. And this is kind of part of his writing style. He'll often use a claim that something is clear or just a reformulation of something else. And it's like, I don't think that's obvious to me. Where did you get that? That is part of his writing style. Let me reread that one more time before we go. To make sure I'm not missing something important here. Yeah, if a squared is even, then a cannot be odd because the square of an odd number is odd. If a squared is odd, then a cannot be even because the square of an even number is even. So in his proof, the entire first sentence could be removed. This is really only a reformulation of the theorem, taking into account ordinary logic. That entire statement is not needed. You don't need that entire sentence. He thinks that he's being helpful by pointing out that it's just another way to view the same theorem. But at times, when he's trying to be helpful and add something like that, it's actually doing a disservice because that can confuse the reader into how do you reformulate a logical statement. So I think I see your confusion as to how do you reformulate it. My mind immediately was going toward the contrapositive or something, but that's not what he's doing here. His proof is identical to mine. This is, I mean, I just wrote it with a little more, like I call them case 1 and case 2. But it's exactly the same proof. It's exactly the same thing. A is either even or odd. A must be even because if it were odd, by the theorem, a squared would be odd. And then in case 2, it's the same thing. A must be odd. Otherwise, a squared would be even. Oh, wait. Yeah, no, this is good. I put this in brackets because this is all where proofwriting is a subjective art at times. Like, this part in a bracket, you could either put or not. Like, do you feel that that's valuable, or do you feel that that's just adding extra noise? There's no clear answer. There's no right answer. Depends on the audience. I think it's valuable, and he thought it was valuable to add that first sentence, but it's a little detracting, and it was confusing for you. So I feel you. Trust me, at times Lang will make you feel stupid with a comment like that. Like, you will see people in the comment section of my videos saying like, "Oh boy, you're reading Lang, huh? I have nightmares about him." His arguments in this book, in his graduate level algebra book, made me feel like I'm an idiot. I don't understand a single thing. This guy thinks that this is obvious, and it's not obvious. Dang. Like, it's a really pretty book, but it's hard. It's hard, and sometimes he'll omit some details or add in some extra words that make you feel like you should understand something that, yeah, is not always obvious to everybody. So this, I would say that that's slightly poor math writing. I would have said the same thing after. I would have, if I were writing that proof, I think that his note is excellent, but I would have just done it after the proof and said, like, notice that this is just a reformulation of the logic, or this is another way of viewing the same theorem. But the real argument didn't depend on that sentence at all. Yeah, hope that makes sense. Thanks. I had a lot of fun today, and this was just terrific exercise, practice for me, teaching and everything with this kind of material that usually you have to have a freaking master's degree or a PhD to be able to teach this stuff. But at least, usually this material is only taught in a college classroom. And to be a college professor, you have to do research and be a research mathematician. I think that's nonsense. I think that we can bring this kind of math to YouTube. So thank you. Thank you for being here, and hope you enjoyed the exercises. I do think I'm going to I'm gonna think about it a bit more because this is a really nice section too. I could work this section for next week's videos, or I could go to induction. I think I'll think about it, but I hope you enjoyed nonetheless. Take care. Bye. Bye.